Hello. In this video, we'll be covering section 1.1 of our series on single and multivariable calculus. Specifically, we'll be introducing the topic of limits. But before we begin discussing limits, we must first talk about tangents and tangent lines. So, as a definition, a tangent line to a curve at a point is one which is in the same direction as the curve at that point. And at this point, the tangent line makes contact with the curve. We'll see some examples below, but just to reiterate the definition, a tangent line to a curve is just a line at a point on a curve that is in the same direction as the curve at that point. Now let's look at some examples of tangent lines. To start, let's consider the plot on the left, which is a circle. When we're considering drawing tangent lines on a plot, you first pick a point. So let's pick this top point here, for example. Then what you do is you imagine drawing a person above that point. And then you draw a dotted line of that person's eyesight. So this person is looking exactly straight when they're standing on this curve. And then what you do is you draw a line which is parallel to this dotted line, the direction this person is looking in, and passes through this purple dot that the person is standing above. So we just draw a line which passes through the purple line and is parallel to this dotted line. So let me adjust this and rotate it. So this is a line which is exactly parallel to the dotted line and passes through the purple dot. So this purple line here is a tangent line to the circle at this point. Similarly, we can consider this blue dot down here. What we do, like before, we draw a person standing above the dot, and we have that person look exactly straight. Then what we want to do to draw a tangent line is we draw a line which is parallel to this purple dotted line and passes through the blue dot. But this orange line already does both of those things. It passes through the blue dot and it's parallel to the purple dotted line. So this orange line is also a tangent line to this circle. Alternatively, we can consider the parabola on the right here. The graph that we wish to find tangents of is the blue one. Then let's consider a point on the left. So we can consider just any point. I'll choose this one. And what we do, just like we did before, we draw a person above that dot and we have them look exactly straight. Then we draw a line which passes through the purple dot and is parallel to this dotted line. Doing so, making sure that the line actually passes through the purple dot and is parallel to the dotted line, we find this purple line here, which is a tangent to the blue curve. Similarly, we can consider this white dot here. Again, we draw a person standing above the dot, and we have them look, let's draw them a bit smaller, and we have them look exactly straight. Then we draw a line which passes through the white dot and is parallel to this purple dotted line. When we do that, we find this orange line. So both the orange and purple lines are tangents to this parabola. What we notice is that tangents are different depending on the point that they pass through. However, we can easily verify if a line is tangent by using this drawing method. There are more rigorous ways of finding tangent lines and verifying that a line is tangent, which you'll see later in this course. But for now, at least as a general idea, this will suffice. What we saw above was one way of viewing tangent lines. Namely, it's the direction that a person would look if they were standing above a certain point on a plot. Alternatively, one can look at tangent lines from the perspective of velocity, which is something that you've experienced in your everyday life and something you may have seen in a physics class before. To set up the problem, consider the two plots here. On the left, we have x, which we'll say is the position of a ball as a function of time. So time is on the x-axis and the position is on the y-axis. As a picture, let's say we have the ground here, and we'll call this point here, we'll call this x is equal to 0. Right, so this is when the position is 0. And we'll have a ball. Well, if you look at the position, it's above 0. So let's put it here. We'll have an orange ball, which is a positive distance away from x is equal to 0. So this plot here shows how the position changes as a function of time. Specifically, what we see here is that the position does not change as a function of time. So given any time t, if you look at where the position is, the position hasn't changed. So the ball is just sitting here. That means the ball has no speed, right? It's not moving left or right or up and down. It's just sitting here. So the speed or the velocity, so v here we'll call the velocity. The velocity here, which is how fast the ball is moving, is 0, right? Because the position is constant, which means it's not moving. So the velocity here is 0 as a function of time. Given any time, how fast the ball is moving is 0. It's not moving at all. And the reason that this tells us something about tangent lines is if you look at the position and you plot the tangent line as a function of time, well, let's consider any point on this plot. Let's say we consider this point. And we draw a person above that dot, and we have them look straight. Then what we want to do is we want to find a line which passes through the blue dot and is parallel to the purple line. Well, one line, and in fact the only line that achieves this, is this purple line I've just drawn. And what we then plot on the velocity is the slope of this line. So the velocity is the slope of the tangent line on the position plot here. So since we see that the plot has a 0 slope for the tangent, right? It's just a straight line, which means it has a slope of 0. That means we plot here the slope, but the slope is equal to 0. So the velocity, or how fast the ball is moving, is 0. Next, let's introduce the topic of limits from the viewpoint of velocities. What we see on the left here is a plot of position as a function of time. So this blue curve here is the position of an object as a function of time. And what we saw above was that if we wanted to compute how fast this object was moving at any given time, we had to find the slope of the tangent line to that plot. But one way to compute a slope on a plot is just to do the rise over run between 2 points. So we just pick 2 points. We'll call them P and Q, as seen here. Then we draw this orange line between those 2 points. And we just compute the rise and the run. Well, the run is given between these two distances. So A and A plus H. We don't know what H is yet, but we'll just say it's the difference between A and A plus H. So that's the run between P and Q. And then we need to compute the rise, which is given by these red X values. So we have X at A, right? So if you plug in for T is equal to A on X, you get this point here. And similarly, if you plug in A plus H to X, you find the Y value, or the X value here, the position, at the T is equal to A plus H value, which is Q's Y position. So we also know the rise, which is the distance between these two red dotted lines. So the slope here would be x of a plus h, right? This value minus x of a. So this value minus this value gives us the distance between the two, divided by h. And the reason that we divide by h is that we have a plus h minus a. And when we do that, the a's cancel with each other, and we're left with h, which is what we have in the denominator as the run, or the horizontal distance between P and Q. But the issue here is that this doesn't give us the slope of a tangent line to x of t at any point, right? Because this orange line passes through 2 points, and we know that a tangent line has to pass through at least 1 point, and at that point, it's the tangent line of the slope of the curve. Here, we want to find the tangent line at point P. So, we want this to point in the same direction as a person would look if they were standing above P. So if we compute this, a person at P looks in this direction. And so a tangent line should look something like this. That's slightly more rotated than that, actually, right? Because we want it to be parallel with this purple line. So it would look something like this, where it passes through the P point. Right, so it looks something like this purple line here. But the issue is, this orange line is nothing like this purple line. And one way to get it to that point is by taking Q very close to P. So we chose Q to be some distance h away from A. So what if we made h very small? Right? If you take h very, very small, Q starts to move down the blue curve until it gets very close to P. And when it gets equal to P, this orange line will match the purple line. And when we take the limit, then we get P is on top of Q, and we get this orange line, which is exactly the purple tangent that we drew over here. So this limit is really, we're taking h going to 0, right? We want the distance between P and Q horizontally to be 0, because when we have that, the orange line coincides with the purple line. But there's an issue with that. Namely, let's look at the slope that we have for the tangent line. As we take h going to 0, we're going to have some number. So if we take h going to 0, we're going to have some number over 0, right? And anything over 0 is undefined. So this presents an issue. And limits are the solution to this issue. What limits do is they allow you to correctly make h very small without the limit, or without this slope here becoming undefined. Now, let's consider limits from the viewpoint of functions. Let's consider the function f of x is equal to x squared minus x plus 2, as given by this blue curve in the xy plane. Then, we wish to find the limit of this function f as we go from the left and the right at the point x is equal to 2. So what we see on these tables to the right here is approaching x is equal to 2 from the left and from the right. And intuitively, if you look at this plot, you could imagine that the f value is going to get very close to 4, no matter what direction we approach from, whether it be x being greater than 2 or x being less than 2. No matter what we do, if we take x values getting closer and closer to 2, we should get an f value, or a y value, of 4. Let's look at the two tables. So the one on the left, this left table here, approaches from the left. So we approach from the left. Whereas on the right here, we approach from the right. So on the left here, we have that x values are less than 2. And as we go down the table, these x values get closer and closer to 2, right? So at x is equal to 1, we're 1 unit away from 2. Whereas when we're at the very end of the table, we're 0.001 units away from 2. And let's look at the f values as x gets very close to 2 from the left. The f values get closer and closer to 4. So at the very end, we have 3.997, which is very close to 4. So we can see that from the left, as x gets closer to 2, f gets closer to 4. And if we approach from the right now, we see that as the x values get closer and closer to 2, so we're originally at 3, and we go all the way down to 2.001. So at 2.001, we're very close to 2. And we see for the f values that they get progressively closer to 4. So when x is very close to 2, specifically when it's 2.001, we have an f value of 4.003. So that's very close to 4. And what we find is that no matter if we go to the right, so we approach from the left, meaning we take an x value here and then here, and we get closer and closer, or if we take it from the right, meaning we start at, let's say x is equal to 3, and we move closer and closer, no matter what direction we move in, the y value is getting closer and closer to 4, as we can see here. So we're getting closer and closer to 4. And that means that the limit of f of x as we go towards 2 is equal to 4. But let's see this in an actual definition. So as a vague definition of a limit, and this is vague because I'm leaving the more rigorous definition for a later section. But as a vague definition, we say that the limit of f of x as x approaches a is equal to L, or in more mathematical notation, this phrase written in the orange box, so LIM, which is short for limit, and then we write underneath LIM, we write x arrow, so x pointing to a. That means x approaches a, and then we're taking the limit of this function, f of x, and we say that that limit is equal to L if we can make values of f of x arbitrarily close to L, as close as we would like, by taking x sufficiently close to a, but not necessarily equal to a. So what does this mean? What we saw before was that we wanted f of x to be arbitrarily close to 4. So in our previous example, we saw that L was equal to 4. And we wanted our f of x to be very close to 4. And the way that we could do this was by taking x very close to 2. So before, we saw that a was equal to 2. And what we found was that when we got x very, very close to 2, f of x was very close to 4. So vaguely, the limit of f of x as x went to a was 4. But again, as a caution, So I'll draw a caution sign. This is vague and imprecise. What I mean by that is, what does it mean by arbitrarily close to L? That's not really well defined. And sufficiently close to A is also not really well defined. So what exactly these two things mean, what exactly arbitrary close to L means and sufficiently close to A means, we'll define in a later section of this series. But for now, this sort of approach is good enough. So let's consider a picture of that vague definition we saw above, because the words themselves aren't very helpful. So let's consider a function given by this blue plot here, which we call f of x, and that's its y value. And this is in the xy plane. Then we said that we want f of x to be arbitrarily close to some L. So arbitrarily close here, we'll say, is within this orange region. So this region we'll call arbitrarily close. So specifically, we want y values of our function to be between these orange regions. So we want y values between this red dot and this red dot. And what the limit means is that when we wish for f of x to be this close to L, so we want our f values to be within this orange region, it means that we can find some x values that give us those exact f values. Here, all of those x values are given within this purple region. So what we do is we just take the first red dot here and we draw a purple line all the way down to here. So this is one x value. That's the lower bound for the x values. And the upper bound for the x values is given by the x value of this red dot. So it's right here. That's the upper bound for the x positions. So what we find is that if x is between these two values, which has a inside of it, that's an important part, that a is inside of these two boundaries. If it's not, then the limit doesn't exist. But the limit exists here, so we have a within these two boundaries, and that means if we pick an x value anywhere between here, so any of this region I just shaded, if we choose any of these x values, we get a y value that's within this orange region. Or namely, it's along this line here. We get one of these x values. And when that happens for a function, we say that its limit going to this certain a position exists and it's equal to L. And that concludes this section introducing the topic of limits. Thank you.